Yeah. The plastic pipe is, some of it's about 20 years old now, and they're just beginning to discover about how plastic changes with time. So we're now beginning to get quite interesting failures as a result of things like shrinkage of the plastic.
Shrinkage?
Yeah. So no. Plastic is always a short-term solution, never a long-term one.
Can we go early, a bit, 10 minutes early?
If you want to go early, that's fine. Because
just leave the lecture because we're going to attend for the Juma and stuff. Friday.
Okay, right, yeah.
Friday.
Yeah. We've actually got far more lecture slots than we need. So it's very easy for me to finish early anyway, if that suits a lot of people. I don't know. Do you think there'll be quite a lot of people who would like to finish early? Shall I get them to take a vote? We can ask them. You are the customers, you get what you want. Is it warm?
Oh, it's beautiful, yeah.
This one's off.
Is it off?
Yeah, that one's they only have two settings, boiling hot and off.
Exactly, yeah, it is roasting.
And then to allow for that, they open the window. The window's open just above you. We're very interested in energy efficiency. Okay, morning everybody. Or good afternoon, should I say, more precisely. One of your colleagues has suggested we might finish early today, which I don't have a problem with, in that we have plenty of lecture slots. What I was going to do was assess the number of people who did actually want to finish at 10 to 2 today. 10 to 1. Looks like it's just you. But we could. I mean, it wouldn't matter because we're running on into semester 2, so we've got plenty of time. Okay, we'll see. Is it just a one-off today, or is it every Friday?
No, I think just time changed, so might be every Friday.
Might be every Friday from now on.
Yeah.
Right. Okay. Right. Oh well, we'll work around it. The other thing was somebody very kindly wrote and asked about lecture notes. I'm old-fashioned in the way I teach. There's a saying, no pain, no gain. You've got to suffer a little bit, I'm afraid, to remember it. And that means writing it down, having a go at it. This is all, apart from the sort of add-on bits, it is all basic electrochemical theory, which is in the books that I mentioned to you. I will put some revision notes up at the end of the day, but I don't believe in spoon feeding people. Here are the notes, and that's partially because the notes become stale. If I just have one set of documents and I just keep putting it out, it just gets stale. It's more interesting to build it as I go along. Okay, and it's more interesting for you as well. I should hasten that. We finished last time just saying that all these corrosion processes are reactions, chemical reactions. They have a thermodynamic energy change, and that is related to the electrode potentials that we measure in the field. So the potentials you measure relate to the reactions that are going on at the anode and cathode. And I think that was our last slide.
Yeah.
Yeah, excellent, good. I have to do that because sometimes I get confused. Right, so that's where we were. What I want to do today is talk a little bit more about electrode potentials. And let's just see whether these are... Okay, these are slightly in a different order. So, in order to measure potentials, we need a standard. And the standard that is used internationally is the hydrogen electrode. So if you take a piece of material, it doesn't really matter whether it's a bit of platinum or whether it's a bit of steel or a bit of plastic. If it's smooth and polished, it's naturally brighter and shiny. If you roughen the surface, it gets darker. Okay, and the ultimate, thank you, is when you've got a very rough surface with a lot of voids between the particles in the surface, then it looks black. And that's all this is. It's a large surface area platinum electrode by making the surface very rough and open. So we have a platinum electrode in 1 molar acid solution, so it's an acidic environment, and we bubble hydrogen gas over the electrode. And the definition, the chosen arbitrary standard, so we've just said it will be 0 millivolts, whatever that voltage is that comes off this laboratory apparatus is the standard. It's not much good in the field though. You may or may not have seen one of these in the lab, but you'll never see one in the field. There are lots of reasons for that. Nobody really wants to be lugging a hydrogen cylinder around the place to provide a source of gas bubbles. Nobody really wants to be handling acid. And the company doesn't want you carrying bits of platinum around the place in case they go missing. So they don't use these at all out in the field. What they use is a series of what they call secondary standards that have a known voltage against the primary standard, against the 0 millivolt standard. And we'll have a look at some of those reference electrodes in a minute. Just yeah, so what you've got on your handout is a sketch like this. And what it's illustrating is the hydrogen electrode, the standard electrode is what we call a half cell. So to your left is the standard hydrogen electrode as 1/2 of the cell. The other half of the cell is the copper electrode, and then the combination of the two together make the whole cell. So quite often you'll see in the text them talking about the half cell reaction. Like all textbook drawings, there's an error in here, and the error is that they are showing or the suggestion of a flow of electrons round the circuit. And the whole point of the voltmeter is it has a high impedance and there shouldn't be any significant electron flow. Okay, so there will be a few nanoamps of current flowing, but that voltmeter should have an impedance of something like 10 to the 6 well, 10 to the 6 ohms anyway, maybe more, and there won't be much current flowing. And that's how you're supposed to measure potentials without a current flowing. In fact, if you draw a current from a reference electrode, any reference electrode, that's really bad news. You can damage the electrode and it stops having its constant value that you measure everything else against. Yeah?
Just question, how, I mean, what is the practical for this one, I mean, practical usage?
You take your standard electrode, not this one, this is the lab one,
Yep.
and a voltmeter, and you can go and measure the potential of your pipe in the field. Okay.
So, if it shows 0, it's okay. I mean, how we can detect the potential?
Measure it on the digital voltmeter.
Okay. So what should we what will it show?
Well, so for example, if you were getting good cathodic protection, you'd want what, about minus 900 millivolts against a copper sulfate electrode. But you're leaping ahead into the application. But the application is to measure the potential on your electrode. Your unknown. Is it being cathodically protected? Is it corroding? What is the potential of this piece of steel in groundwater, or in this case in the lab with the copper plate indicator? And we measure it against a standard using a high impedance voltmeter. So, and as I say, the description is this is a half cell and that's a half cell, and the combination is the whole cell. Okay. Let's check that. Yeah, that's all right. Previous. What you're measuring, we've been calling it voltage. The laboratory name for it is electromotive force, EMF. And what you find in the literature are tables of EMF values. And what you've got in your handout is a little sample of a small part of one of those EMF tables. Okay. And that's more or less what you've got on your handout. This might be a slightly different selection of metals. Yeah, it is. But there are. If you go to the reference books, you get these tables. Here's the hydrogen electrode, 0 millivolts. And everything else is measured against it. So some things are less reactive, like gold and platinum and silver, above 0, and other things are more reactive, like zinc and aluminium and magnesium and sodium and potassium. So reactive materials are down the bottom, and reactive materials are above 0 in the table. Once you've got a table like this of thermodynamic data, you're then able to make any combination of two half cells to work out the voltage on the full cell. So we'll do it in a minute, but if you imagine combining in a galvanic couple some zinc with some iron, or some iron and some copper, then we can take the values off this table and calculate out the new cell voltage without having to measure it again from scratch. Okay. See what the next one is. Oops, might have done that. Don't do that. Yes, okay. So this is just a sketch, which you don't really need the details of. It's symbolic in some respects, just showing that you will get a potential when you join an iron half cell to a copper half cell. And again, this drawing is incorrect because it's showing electron flow through the voltmeter, which would be very small, and in fact the amount of corrosion of the iron and the amount of plating out of copper on the cathode would be small, because that's a voltmeter. If you wanted to get significant change in the electrodes, oxidation and reduction of the electrodes, that would have to be an ammeter. And then you can measure the current flow and determine the speed of the corrosion that was going on. So you're able to get cell voltages from this thermodynamic data. Okay. And this is the converse one. As I say, you don't need the details of the diagram. This, in this case, the iron now is the cathode, and the zinc is the anode, where previously the iron would be the anode. So the current's now flowing in the opposite direction of the speed of an ammeter, and the voltage is different. Okay. This is just a cross-section of one of the more commonly used electrodes. It's still not the most common, and I'll give you a section of another one in a minute. But this is the what they call the calomel electrode. It's actually a mercury chloride electrode, but the electrodes all have some basic features in common. So they're quite often a plastic tube now, and at the bottom is a porous sprit, a link between the solution within the chamber and the environment, and the groundwater or whatever your electrolyte is. And this electrode has a known voltage against the international standard. So I can tell you it's 241 millivolts against the standard hydrogen electrode at room temperature. There are temperature correction tables, but you don't really need to know about that at this stage. The point is, I could measure a voltage in an environment using this sort of electrode and then correct it to SHE. I can pass that round. As I say, I've taken the solution out of it just in case anybody dropped it. The tube now in commercial ones is plastic, but the idea of having a body with a porous frit on the end, a single lead coming out to go to your digital voltmeter, is the standard format for these things. Just check. That's all right. So, are you all right, folks? Does it make sense? Any question? No? All right? Okay. If you wanted to work out the potential between two half cells, in this case I've just taken the values for off your table. So for silver it's 0.799, and for iron it's well, you've got 0.440 on your table, and I've got 0.447 on mine. So there's a slight variation in the table. All you do is subtract one from the other, and you've got to remember that there's minus minus, so that's plus.
So it has to be the cathodic minus the anodic.
It is, let's just check that. It is the cathodic minus the anodic, yeah. The reduction minus the oxidation. And as I say, in your table you've got 0.440 for the iron reaction in your table. And so the calculation gives you the cell voltage, the potential difference between your two metals in the environment, and indicates the thermodynamic viability of the reaction, but it doesn't tell you how fast it occurs. And if you're interested in lifetimes of components, there's the speed of the process that's also important. Thank you. Okay. So, we've got a laboratory standard, we've got tables of electromotive force that give us ranking in reactivity of the material and allow us to work out the new cell voltage for any combinations of different elements. The applied version of it is this thing, the galvanic series, where instead of using pure elements, zinc, tin, iron and so on, we were actually using alloys. And instead of doing the work in 1 molar standard acid environment, we're now actually doing the measurements in a particular environment, in this case seawater. So we've now got a ranking, and there would be millivolt values if in the books for particular alloys against the hydrogen electrode. And the same thing happens as you get in the EMF table. The unreactive materials, the noble materials, are at the top of the table with the more positive potentials, and the reactive materials are at the bottom of the table with the more negative potentials. And so we can actually go to the books and look up information for our specific materials in our specific environments. So you've got away from the sort of standard pure lab condition. One of the things that perhaps this talk about the potentials brings out is if anybody quotes a potential, and people do all the time, it's so many, actually that must be volts, wasn't it? Not millivolts. It would be 444 millivolts, wouldn't it? If they quote a potential, that's almost useless unless it says it's what it's been measured against. Okay, they may have corrected it back to the standard hydrogen value, or they may have just taken the value off the voltmeter, in which case it could be, in the case of the electrode that went round, it might be saturated calomel electrode, or the value may have been measured against a copper-copper sulfate electrode. You've got to say what your voltage is measured against. Otherwise, people start guessing, and the values get fouled up. And it's quite common. It's surprising how common it is. Somebody just measures a voltage and forgets to say what they measured it against, and fail to convert it back. What we say in the labs, we like people to convert it back to the standard scale. In industry, quite often they just settle for whatever the most common reference electrode is they're using in the field, which is copper-copper sulfate in your case. There are tables of data. You can measure the potentials. You need to quote them against the appropriate primary or secondary standard. Okay. Let's see what the next one says. Field measurements, that's all right. Not wildly in focus, but what you've got in your handout is a cross-section of one of the copper-copper sulfate electrodes that's quite commonly used for field measurements. So there's a copper rod. This is the container. As I say, it's often a plastic rather than a glass sleeve. There's a porous sprit at the bottom, porous plug as they've called it, which allows some electron exchange between the solution within the chamber and the groundwater outside, and that electrode has a standard potential against the standard hydrogen. zero value. And then the sort of things that you can do with that, this is a section showing a plot of potential round a pipe. So this pipe is coming horizontally out through the board, and this is the field in the earth around the pipe. And that's measured by having one contact on the pipe, one contact on the reference electrode, and using a voltmeter to measure the potential at various fixed distances away from the pipe, and then plotting the graph. So you can get potential field data, and that gets interesting once you start getting pipe lines intersecting each other. So you want to know what the potential gradient is around your pipe, and you want to know whether your pipe field is affecting somebody else's pipe. That's also very common in places like the UK, where we've got pipes intersecting all over the place. So we can measure the potentials and start using the data. What we've got on the other side of the handout is this little plot, which is just to illustrate the changes in values that you get using different reference electrodes. So this is the copper sulfate electrode. Then we've got the standard hydrogen electrode. And lastly, we've got another standard that's used sometimes, and that's the zinc and seawater electrode. The point is, when we get into our zone of cathodic protection, where we're happy that the steel is not going to corrode, that's 0.9 volts against the copper sulfate. It's actually only about 0.6 against the standard hydrogen, and it's only minus 0.2 against the zinc in seawater. So you've got to make sure that you quote the right reference electrode so you know where your values are coming from. Okay. Yeah.
Is this list, is it always true, or like will different books have like different zones for the cathodic protection?
This is for pipeline steel in mildly alkaline environments. So it'd be true in seawater, it'd be true in carbonate bicarbonate solution groundwaters. It's, you know, they're giving you a zone of about 100 millivolts to allow for that. It's obviously not true for a piece of stainless steel or an aluminium alloy, or so there are different charts for different materials and in different extremes of environment. But this is some of the common data for, you know, if you were asked about a piece of pipeline steel, you would plumb for one of these values. It would be fine. Unless it somehow got into some weird environment other than a groundwater, or and then you start to have to, if the environment was more aggressive, you'd have to put more cathodic protection on. If it was less aggressive, you could save money by turning the cathodic protection down a bit. So it's quite useful data in that sense. But the reason why I'm showing it to you is just to say, if somebody quotes this value as the measured potential, it's actually that on the standard hydrogen scale, and there's actually this on the other electrode. So you've got to be careful about the electrode selection. Okay. When we were talking the other day about the microcells and things, we said that the pH of the environment around the anode and cathode changed, and you get increasing acidity around anodes and you get increasing alkalinity around cathodes, providing there isn't solution flow causing refreshment and taking the products away. So you can measure the pH near the in the system and look for the localized alkalinity and acidity at the cathode and anode. That actually is a pH electrode. So it would be used in conjunction with one of those reference electrodes to probe an area for pH, and the active part is this glass, special glass filament's not quite the right word, but special glass end to this sleeved probe. That one still has fluid in it, so don't snap it, but they're quite hardy, robust and portable components that allow you to look at pH. And that's what I want to talk to you about next, is to say a little bit about pH. Machine will behave itself. So we tend to think that acidity enhances corrosion. That's certainly true for iron, for steels, but quite a lot of materials get attacked in alkali, so aluminium alloys particularly, and at high alkali values, stainless steels are also sensitive to attack in alkali. So there are risks at high alkalinity, and there are risks at high acidity for a variety of alloys. The relationship between the standard potentials, which we've got on our EMF scale, and what you see in the real cell can be calculated out using this adjustment for the change in acidity. The negative log of the, well, it says H+, but of course H+ is a proton, so the real ion that's in there is that one, which is the hydronium ion, and that is your acidity. If you calculate out this little bracket here, then that comes out at 59 millivolts per pH unit at room temperature. So for every 1 pH unit change in the acidity, the cell potential is going to move by 59 millivolts. it's because it's the log, so your pH is running from 0 to 14, and you're getting, as the pH changes, one pH change is 1 times the bracket, which is 59 millivolts. So we've got a thermodynamic measure of how the pH changes the potential. That's fine, so we can now make a correction. And what's happened is that the guys have done the calculations and plotted the data. And these things get called quite popularly Courbet diagrams, because a French corrosion chemist made a couple of atlases of the diagrams, but more correctly they should just be called potential pH diagrams. And they're giving you thermodynamic data, but no kinetic information. Thank you. Once you start looking at these diagrams, you begin to see that they have some characteristic pattern to them, and what we find is that you've got an immune region where no corrosion occurs at negative potentials. You've got a corrosion region where thermodynamically you're going to get attack, and quite often there's in the middle pH range there's a region of passivity where some sort of protective film has been created on the surface of the material. Okay, let's take a quick look at one of these diagrams that you've got on your handout. So you've got potential against pH on your handout, and what this diagram's showing is as you go to lower potentials, then the ion is the stable form. So this is the immune region where no corrosion is occurring, immunity down here. At higher potentials, you go more anodic, then you begin to get corrosion, and these shaded regions here, and also at high alkaline pH over here, are the corrosion regions for the steel. And then in this intermediate region here, you've actually grown a film of Fe3O4, which is magnetite, black oxide, and that actually is passivating. So we've got immune, corrosion over here at this end as well, the shaded areas of corrosion, and passivity in this middle region here. Okay. And that's common for quite a lot of the diagrams. Diagrams, different shapes for different metals, but you'll find these three regions somewhere on the plot, and in this case actually two corrosion regions, one at low pH and one at high pH. Okay, we'll talk a little bit more about these next time. Yeah, sorry.
The passivity. What you said you wanted to
Where this Fe3O4 is, yeah. That's a passive layer. So this just starts to corrode, and then it blocks off any further corrosion. Yeah.
The
Okay.
Fe2O3, what's going on there?
Fe2O3 is porous. You can get that at as it indicates at higher potentials, but it's a porous film rather than a passive film. So that's brown rust. It just carries on corroding. Yeah.
And if that's the case, I need to quickly pop the cards
It's a little.
Yeah. So this is passivated. That's fine. Here you get some. You start to get some corrosion because the Fe2O3 is porous, so it won't actually stop. In a sense, it's as you move more anodically, you're going to get more corrosion generally. So this is actually really. I know it's not shaded in, but this isn't passive. It is tending to corrode as you go.
Okay, this
is
with
passive.
Yeah. Okay, this with the time. This one transforms with increase in the peak.
No, this is showing you what happens if you take a sample and hold it at this potential at this pH. It doesn't show how it will change if you move it. No, Fe3O4 is stable, so it will just stay unless. Maybe over a long period of time. but it doesn't tell you anything about the speed of the processes. This is thermodynamic data. It just says
At a certain
if you go
instant.
there, then a piece of steel will corrode. If you go here, it won't corrode. If you go here, it will pass.
But if you
Okay. Thank you. You're welcome. Cheers now.
Okay. Are you gonna find it?
Is a degree
Professor,
Hello.
I was thinking about the topic for my dissertation,
Okay,
and
yeah.
I'm really interested in doing something with corrosion.
Right.
So I was thinking something like cathodic protection.
Right.
Yeah, but the thing is that I don't really have like experience in the field.
Okay.
I don't feel
So, what I say to people is, you should do a project that's going to help you get a job. So, if you want to work in cathodic protection, then doing a project with your CP makes sense. You should do a project that plays to some of your strengths. So if you're good at mathematical modelling, then you should do a mathematical model. If you're good at data analysis, then you should, if you're good at lab work, you should do a lab work. So the first thing is to think about what your strengths are and where you want to get a job. Because you can put on your CV that I did my final project on whatever, and it sort of adds to the value. There's quite a lot of interest in cathodic protection. What I look at are things like when the protection goes wrong. So when you get overprotection, you start getting hydrogen embrittlement. So that's one of the things that I look at. Thanks. So we could,
So like everyone sat there for about 20 minutes and nothing happened.
I'll go to the test. So I'll go over the components. I will describe like the manuals and the cups. Then you can just move on.